we say that an element in the integers mod nz is a unit if there's a solution to the equation ax equals 1. And just a second, let me increase the contrast. There we go. And so this is also equivalent to saying that there exists some element b so that when you multiply a and b, you get 1. And so we call b the inverse of a. So if we consider this definition, let's find all of the units in z mod 8z. Well, we're going to have to figure out if all of these equations have solutions. So by abusive notation, I'm going to use the same x every time. So we're going to have 0 times x equals 1. We'll have 1 times x equals 1. 2 times x equals 1. 3 times x equals 1. 4 times x equals 1. Okay, actually let me space these out a little bit more. And I think I'll actually use I'll use like an x0 here. So we're trying to see if this equation has a solution. And the answer is no. There's no number that we can multiply 0 by to get 1 in any set. So next, let's consider the equation 1 times x1 equals 1. Well, this has a solution. Namely, we let x1 equal 1. So 1 is going to be a unit in z mod 8z. Now we consider the next equation. Does 2 times some x2 equal 1? Well, now we have to think about it. If we go through each element in the set, we see that there is not going to be a solution. And I leave that to you to verify. And next we try 3 times x3 equals 1. And we want to see if this has a solution. And so it is, namely, if we choose x equals 3, we get that 3 times 3 is 9, and 9 is congruent to 1 mod 8. So right now we see that 1 and 3 are integers. So now we move on. So we want to see if 4, and I meant to say 1 and 3 are units, not integers. Well, they are integers, but in this sense, they are equivalence classes or congruence classes that we are saying represent units in this set. So now let's see, we've got 4 times x4 equals 1. Is this a unit? No, this does not have a solution. Once again, I asked you to verify independently. So we move to the next equation, which is 5 times x5 equals 1, and we want to see if this has a solution. So it does, namely x equals 5 is going to work because 5 times 5 is 25. 25 is congruent to 1 mod 8. So we're almost done. Now we try 6 times x6 equals 1, and that is not going to have a solution. And the last thing we'll try will be 7 times some x7 to see if this has a solution. And it turns out that it does. This one is going to have a solution of x7 equals 7. Because 7 times 7 is 49. 49 is congruent to 1 mod 8. So this tells us that the units, so the units of z mod 8z are 1, 3, 5, and 7. And we were able to find that by using the definition. It's a bit tedious, but we were able to use it to determine all of the units in this set. So now we get the following theorem. And this gives us a different way to characterize units. We're given that an element A is a unit in Z mod NZ if and only if A and N are relatively prime as integers. And so how can we use that? So if we look back at this same example, find all of the units in Z mod 8Z, we know that units are going to be, let's see, we can write this down. The units in Z mod 8Z will be congruence classes A, where A and N are relatively prime. Okay, so what we're looking for basically are the set of all elements less than or equal to 8 that are relatively prime to 8. So that's going to be the following. Let's see. 0 doesn't work. 1 works. 2 doesn't work. 2 is not relatively prime to 8, but 3 works. 5 works. 6 does not. They share a factor of 2, but 7 works. So we see that, so 7, so these are the units in Z mod 8Z. Since 1 and 8 equals 3, 8 equals 5, 8 equals 7, 8 equals 1. And so each of these, I'm representing the 1 and the 8, these pairs, these represent the greatest common divisor. Remember, that's the notation that we use. So since each of these numbers is relatively prime to 8 in the integers, their congruence classes are units in the integers mod 8.